Good morning. Today we're looking at section 7.3, Le Chatelier's principle. Le Chatelier's principle was developed by Henri Le Chatelier, who lived from 1850 to 1936, a French chemist and engineer who worked in chemical industries. To maximize the yield of products, Le Chatelier used trial and error. What we're able to do is look at Le Chatelier's principle and make some predictions about products. What's important about that is he worked at a factory. He was trying to do something practical with chemistry. He was trying to improve the yield, essentially trying to improve his profit. So this is important because we can take his principles that he applied in the chemical industry setting and then look at what happens in the human body and look what happens with medication and other things. We'll see that in the organic unit. Essentially, Le Chatelier's principle states that when stress is applied to a system at equilibrium, the system will adjust to undo that stress. Imagine yourself in the teeter-totter. You're on one side, a friend's on the other, and as someone walks by, they throw your friend a large bag of potatoes. Immediately, the teeter-totter starts going down in that direction. In order to compensate, you are going to adjust by leaning back, and your shift in weight will undo that stress, and the teeter-totter will return to a balance or an equilibrium. Chemical systems work the same way. Chemical systems want to maintain that equilibrium. If you put pressure on a system, the chemicals will shift to undo that stress. Think about your own life. The past couple weeks, you guys have been stuck in kind of a unique situation here with quarantine and whatnot. So as a result, you've had additional stress put on your life. You've probably done things to undo that stress. Some people have a treadmill, they go running in the basement. Other people will watch a whole lot of Netflix. Other people will start eating more ice cream. People respond to things in a different way. But the whole thing is if stress is applied, you're going to undo that stress. In a normal school situation, when stress is applied by your courses, people go to the gym. People will cut back on working hours. They'll call in sick to work. They'll start skipping class to get other work done. You're trying to undo that stress. Your body needs some stress to function, but too much stress causes people to have other types of challenges and issues. So some stress is a good thing, too much, not very good. All right. So Le Chatelier's principle, let's see how this applies to chemical systems. So let's consider a reaction that starts off with only reactants, and as the reaction progresses, it reaches equilibrium, but the reaction doesn't go to completion. It ends up leveling off somewhere around there. If we start with a larger system or a higher concentration, we end up with the same type of shape. We expect the reaction to be quick at the beginning, and then it starts leveling off, but the reaction again doesn't go to completion. We see a higher concentration of reactants at equilibrium because the system's larger. Let's say we add this in two parts. The first part goes down and equilibrates. Once this happens, we add some more, and then when that occurs, it equilibrates again. Now what we see here is that whether we add it in two separate steps, one step and two steps, the system overall is this larger size. Consequently, equilibrium is at the same position. So it doesn't matter how we add the reactants. Based on the size of system, the equilibrium positions are going to be the same. In the first graph, we know that we have no product initially. As the reaction progresses, we make product, it then comes up and it levels off at some point. It's not important these lines meet because these are concentration lines, not rate lines. Concentrations don't have to be the same at equilibrium. In the second scenario, the concentration line comes up and it goes a little bit higher, but it still levels off. And if we look at the ratio between these lines here and these lines here, they would be the same ratio. And that's because the KQ value, product over reactants, will be the same for a small system and a large system, assuming the reactants and products are equal. Finally, let's look at adding the system in two parts. When we added the reactants in two parts, we initially had the smaller reaction leveling off, and then we added a whole lot more reactant, which allowed product to be generated quickly. We end up leveling off to about the same level as we had before. The level don't quite line up perfectly, but we can see the general idea here. The larger system, whether it's added in two parts or one part, ends up with the same KQ value. So for each graph now, let's take a quick look at KQ and what it represents. So KQ is products over reactants. So products have an equilibrium concentration. Reactants have an equilibrium concentration. Here we see our KQ value is going to be a ratio of products to reactants. Products has a lower concentration than reactants, so our KQ value must be less than 1. I'm going to put it down as being a half, just for argument's sake. In this case here, we see the same type of process emerging. Although the values are much larger, we're going to end up with the same ratio. If we put in numbers, we could say, well, this is larger, so maybe it's 2 over 4. That still gives us the same KQ value of 1/2. The ratio here and the ratio here are the same. When we added it in 2 parts, the same thing emerges. We have a ratio here. We have a ratio here of equilibrium. The lines are not straight. We have a ratio here and here. That gives us a KQ of 1/2. We have new products and reactants where we have the same ratio, the 2 over 4, or essentially 1/2 again. So it doesn't matter whether we add the system in 2 parts or all at once, the end result is the same. We end up with a system that has the same KQ value. Remember, KQ is a property of the system at a particular set of conditions. Here, we have initially a high rate of reaction, and that high rate of reaction is a result of our reaction going quickly because of a high concentration of reactant. It's going to go, it's going to level out, and it's going to reach an equilibrium. This is important because it's going to reach an equilibrium with, or when I should say, the rate of the reverse reaction ends up being the same. The definition of equilibrium is the rate of the forward equals the rate of the reverse. So when the rate of the forward reaction equals the rate of the reverse reaction, we have equilibrium. So somewhere around this point here, dynamic equilibrium is established. The reaction is proceeding in both directions, but there's no net change. Looking at our second scenario, what we can see is that our initial rate is much higher. We have a bigger system. The reaction is going to proceed and level off at some point, much like the reverse reaction. The reverse reaction is non-existent initially. We have no product. But as product is formed, the reverse reaction speeds up and eventually levels off at a very consistent rate. Again, we establish that dynamic equilibrium. Actually, a little bit further on, looks like about here. So we establish dynamic equilibrium. The rate of the forward reaction equals the rate of the reverse reaction, the definition of equilibrium. In our third and final system, it's a little bit different. So what we end up having is the rate of the forward reaction is the same as we saw previously. The rate of the reverse reaction is the same as we saw previously as well. The 2 lines meet, showing that dynamic equilibrium has been established. Once we add additional reactant, we have a jump in the rate of that forward reaction. The forward reaction increases in speed, but then as reactants are used up, that level bounces off again to the same thing we saw before, or I should say the same level we saw before. The reverse reaction experiences a quick jump as well, but it too levels off at that equilibrium level. At equilibrium, regardless of how the chemical was added, the equilibrium rate, KQ, the rate of the forward to the reverse reaction, is going to be the same. The system retains equilibrium position. It reestablishes that by shifting products to reactants and reactants to products. The same thing would happen if we removed product. If you have constant product removal, the system continually shifts to make more product to reestablish KQ. This is important because if you have an unfavorable chemical reaction, by removing product, you can drive the reaction to completion even though it's unfavorable, because the system will continually make those products, even in small concentrations, if the product that's already been produced has been removed from the system. So looking at Le Chatelier's principle and temperature, the key thing to remember here is that in this system, we're going to treat energy as if it were a reactant, or a product for that matter. This is important because although energy is not part of our equilibrium expression, it still affects the teeter-totter. So using our teeter-totter analogy from before, we have nitrogen as dinitrogen tetroxide, and we have energy on this side. We have products of nitrogen dioxide. There's two there. We'll show both of them. If we were to add a lot more energy on this side, what we're going to notice is that this side becomes much heavier and would start sinking. Consequently, the system will use this energy to take a reactant and convert it to product over there. When this side becomes lighter, quote unquote, we end up having a reestablishment of equilibrium. So we treat energy as if it were a reactant because it causes the reactants to become products. Likewise, in an exothermic reaction, if you add energy to an exothermic reaction, the system will work in reverse. This means that adding energy to a reaction will not always speed it up. Previously, in grade 9, 10, and 11, we talked about surface area, we talked about mixing and stirring and adding energy because they speed up chemical reactions. We're seeing here now, and this is predominantly in gaseous systems, that adding energy to a chemical reaction may not speed up the reaction. In fact, adding energy could cause the reaction to go in reverse. For Le Chatelier's principle and concentration, let's look at a specific example. The ionization of acetic acid, the covalent acetic acid becoming ions, happens, but it's unfavorable. The majority of this process will remain as reactant. Very few products are formed. Consequently, our equilibrium graph tends to look a little bit like that, where not a whole lot is happening. I'll make that a little bit darker for you. We end up having a little bit forming, but then it levels off pretty quick. Likewise, a little bit of product forms, but it levels off pretty quick. When we add more reactant, we see initial spike in that reactant concentration. It's still going to level off pretty much at the same value we had before. A little bit more product is made, but it essentially levels off at the same value as well. What we see here is that our KQ ratios are being preserved. Products compared to reactants. This ratio here is conserved. The same ratios we see over here and over here. The system's larger, KQ remains the same. Now that's a strong advertisement for typing. So KQ remains the same. Doesn't matter how we add it. In case of acetic acid, it's the same thing as our general example 5 minutes ago. So which of these systems is affected by a change in pressure? Well, we've sort of been led to believe that increasing pressure makes a chemical reaction go forward, sort of like increasing the temperature. But we saw that with energy, that's not always the case. Increasing energy could actually cause a reaction to go in reverse. Here, pressure sort of works the same way. What we do, though, know is that Le Chatelier's principle wants to undo stress applied to a system. So if we increase pressure, the system is going to want to undo that pressure. In this case over here, we have 2 moles of reactants and we have 2 moles of product. In this system, forgive that non-subscript 2, we have 3 moles of product, we have 2 moles of reactant. If we had a specific container, and in this container we put pressure on and we compress this container, what we would see happening is that this system, the second system B, has the ability to shift itself to the side with fewer moles. If the pressure drops and the number of moles drops, we end up retaining equilibrium because we end up having a comparable concentration. We've decreased the pressure, we've decreased the number of moles. So it turns out that system B is affected by a change in pressure because the system will shift to the product to reduce the number of moles, thereby maintaining pressure. If you were to compress system A, a shift in either direction doesn't change the number of moles. So this system can't respond in a way that undoes that stress of the increased pressure. Le Chatelier's principle and the catalyst. Consider the uncatalyzed reaction here reaches equilibrium. With a catalyst by definition speeds up the reaction. It's going to be very, very steep, and it's going to establish equilibrium very, very quickly. Le Chatelier's principle. We talked about how Le Chatelier's principle explains why chemical systems resist change, whether that change is applied in the form of a temperature change in concentration, change in pressure. We see the system resist that change. Catalysts were a little bit different. Equilibrium is established a bit quicker. Anyways, if you have any questions about this, once you've read 7.3, definitely let me know. There's quite a few graphs in 7.3 that I would like to draw your attention to, especially the example on page 452. If you get that example, you're in great shape. Anyways, you've done well today. There's a lot of information here. Read the textbook, watch some videos. I'll post more stuff about Le Chateliers tomorrow, an ed puzzle, a few things like that. Then Wednesday, we'll move on to some calculations. You're doing well. Don't give up. Anything comes up, let me know. Post in Google Classroom or send me an email. Talk soon.